Hi, I'm Craig Given.
I'm Brooklyn Vanderwolde.
Our project was to develop a CPR simulator and was sponsored by Dr. Meserly.
The motivation for our project comes from the fact that there are very few anatomical heart models that exist capable of demonstrating the physiological processes occurring throughout the body. When a person practices CPR, they need to apply over 100 pounds of force to the heart at a rate of 100 to 120 compressions per minute in order to compress the chest approximately 2 to 2.4 inches.
So the goal of our project is to develop a CPR simulator that demonstrates the importance of unidirectional valves and the blood flow through the heart, as well as have a rib cage that will simulate the accurate force required to perform CPR, as well as have a feedback system that gives feedback on the depth of compressions as well as the rate at which those compressions are given during CPR. Our success would be to have 4 transparent valves that show the blood flowing through each chamber, a rib cage that offers 100 pounds of force of resistance when compressed 2 to 2.4 inches, as well as our feedback system giving them feedback on their CPR skills.
The heart chambers are made out of strong, flexible, and transparent silicone. To produce these, we made a mold which can be seen in picture A. The mold itself was printed using a standard PLA filament, and the insert inside was a dissolvable PVA filament. Along the bottom, you can see the more than 9 iterations we went through, with the final one being on the right-hand side labeled C. To produce these, we injected the silicone into the mold using a large syringe. This was then placed in a vacuum chamber and put on a shaker plate to remove the bubbles. After the silicone was fully cured, it was placed in a warm water bath to dissolve the PVA. The external part of the one-way valves was made out of clear acrylic rod. On the inside, there was a stainless steel ball and stainless steel spring. The acrylic was mainly machined on a lathe, which you can see in the top right-hand corner, and once all the components were ready, they were assembled and glued together to create a tight seal.
So for our rib cage, we used POM plastic, a flat steel bar, and some wood to construct a mold for our rib cage. How we did this was first we constructed a 3D model of it in SolidWorks. We then sent that flat pattern and the plastic to go get water jet cut. Once that was done, we assembled the wood into our mold and then heated the plastic up over that mold and bent it into the correct form. And then we added the flat steel bar underneath the sternum to add additional support to our rib cage.
Finite element analysis was performed on the rib cage to estimate stress levels as well as force required. From there, Hooke's law was used to determine the stiffness of springs that would be needed, and then after that, compression tests were completed to analyze the actual force needed.
For our feedback system, we used an Arduino, an infrared transducer, a buzzer for the audio portion of it, and we also had LEDs and an LCD screen that would give feedback to the person performing CPR. The LEDs would light up, red being that they are going at either too fast or too deep. Yellow would mean that they're going too slow or not pushing deep enough, and green would mean that they are going at a correct depth and rate. The LCD screen would also display the actual depth and rate at which they are performing CPR.
The final prototype includes a transparent heart composed of 4 chambers with 2 sets of unidirectional valves, which allows the user to see the fluid flowing throughout the model. The rib cage provides the resistance necessary to simulate the force required to administer the life-saving compressions. And we also have a feedback mechanism which provides visual and auditory feedback of force and depth of compressions and is also data logged. And then you can see the overall assembly of the model in the lower right-hand corner, which also includes 2 reservoirs which the fluid flows throughout. The FEA results show that the stress levels were within an acceptable range, and then the compression tests performed on the rib cage show that about 150 pounds is required to compress the rib cage by 2 inches, as seen in the graph on the lower left.
So for human impact, performing CPR incorrectly could result in death or permanent damage to the victim. So our product will enable people to practice CPR on a more realistic CPR dummy so that they have a better idea of what will need to be required of them when performing actual CPR.
This product is marketed as non-consumer. This is because it will be primarily purchased by entities such as educators, schools and universities, hospitals, and other people that train in CPR. And there's also a ton of potential here because the market's very stagnant and there hasn't been much innovation in the recent years. And there's a current trend that the people want more responsiveness and feedback in their dummies. We've entered this in several competitions. The Brookings business plan we placed in, Brookings idea competition we won first place, and the giant vision competition we came in second. So there's other people that believe in this idea and think it will work. Our estimated budget to begin with was $500 for building our first prototype. It came in at $450, and we believe we should be able to sell these for $1,200 a piece.
In conclusion, the visual CPR simulator was developed, which demonstrates the heart's one-way blood flow and incorporates complex feedback of rate and depth. A few more components are still required in order to assemble the final product, which were not feasible this semester due to COVID-19 complications. However, individual subtesting of components provided validity for the solution and will be able to be easily completed and assembled once complications are resolved.